Welcome to the zoo of continuous functions. So in this video we would like to recollect functions where we know that they are continuous. And you will see that in this video we'll meet all our good friends which we know so well and which we have worked so well with. For example, the sine function, sine x, or the cosine function, or even e to the x. Okay, let's look at this. So first of all, I'm interested of making new functions out of old ones. So I assume f and g are two continuous functions in a and c is a constant, and then I can do addition, subtraction, multiplication by a constant, multiplication of functions, and division by functions, and this all gives continuous functions, well, as long as I don't divide by 0. Same condition always. So let's look at some biological motivations for these cases. So for example, if I look at addition, okay, this could happen if I look at juvenile and adult salmon, and maybe I have measured juvenile and adult salmon separately, and now I'm interested in how much of those occupy a river ecosystem together. So then I would be faced with addition of two continuous functions. Or subtractions can arise easily too. So for example here, if you measure all mutations in a cell line and subtract those mutations which are not cancerous, what you keep is those mutations which are cancerous, and of course this is of high interest to many researchers. The product arises, for example, if you are interested in how many eggs does a frog population produce, where the number of frogs and the number of eggs per frog has been measured, but maybe the product has not been measured, so then you do this. And finally the ratio. There's a very nice example which is the body mass index, right, where you have the body mass divided by the height of the person squared. So here's a little typo. Let's get this fixed. So here's the following theorem which summarizes the zoo of continuous functions. So let's call this the zoo theorem. And the following functions are continuous in their domain. So now this is a very important thing which I will highlight through the rest of the video quite a bit, and must be in their domain. But then we have polynomials, we have rational functions, we have power functions, we have root functions, we have exponential functions and logarithmic functions, and we have trig functions. Alright, that's a bit fast. So let's look at these cases in a bit more detail. Let's do one example each of these cases. So polynomials are of the form, for example, x to the 5 plus 3x squared plus 1. Polynomials always have full domain. So the domain is minus to plus infinity, which means polynomials are continuous on minus to plus infinity. Let's look at rational functions. Rational functions are fractions of polynomials. So for example, x squared plus 3 divided by x plus 1. That would be a rational function. And here the domain is always restricted by the zeros of the denominator. So in this case, the denominator is equal to 0 for x is equal to 1. So we have to take that out of the domain. Power and root functions. For example, one power function would be x to the 5, which can actually be classified as a polynomial if you want to. So it has the same domain. But there are other powers which do not have the full domain. For example, the power to the 1/2, which is the square root function, which has as domain the non-negative values. So the square root function will be continuous for all non-negative values of x. Exponential and logarithmic functions. The exponential function e to the x has a domain minus to plus infinity. The natural logarithm has a domain from 0 to infinity, where now 0 is not included. And then finally the trig functions. For example, sine x, cosine x, they have full domain, minus infinity to plus infinity. Tan x, well, tan x is different, right? It is sine divided by cosine, so it has a vertical asymptote whenever cosine is equal to 0. So maybe for now I write complicated domain, but later we will look at this case in a bit more detail. But here first is another example. So where is the following function continuous? Justify your answer. So if we have like a ratio of functions, which include logarithmic and exponential functions, we have to go stepwise. So let's look at the log first. So the log of x is continuous in 0 to infinity, right? It is continuous in its domain, and the domain is 0 to infinity. Now the exponential function e to the minus x is continuous in minus to plus infinity. So together, this makes the numerator to be continuous, well, in the smaller of the two domains, so in 0 to infinity. Let's look at the denominator. So x squared minus 9 is continuous in the whole domain from minus to plus infinity. However, it can be 0 and it's in the denominator. So x squared minus 9 is 0 for x is equal to minus 3 and x is equal to plus 3. Now the case of x minus 3 does not arise. This is not important because of this. Okay, so we know already that x can only be positive, otherwise the log function would not be defined. So the possibility x is minus 3 can be removed. So what do we keep? F of x is continuous on 0 to 3 union 3 to infinity. That's it. Next example. Yeah, here is the tangent function, finally. Very good. So right, we know tangent is sine divided by cosine. Sine of x divided by cos x. And the domain for sine and the domain for cosine are all real numbers. However, cosine gets 0, right? Cosine is 0 where? Well, at odd multiples of pi over 2. Let's write this down. So I sometimes write it like this. Odd number times pi over 2. If you want to be mathematically more precise, you write something like 2n minus 1 times pi over 2. So which means we have to take these values out because the denominator is equal to 0. F of x is continuous on, well, all these unions. Let me indicate this here. So we can take this interval and this interval and this interval and the next one where we have to take out the minus 3 pi over 2 or minus pi over 2 or pi over 2 or 3 pi over 2. So how do we write this down? Well, let's maybe start in the middle and then we can work ourselves to the left and to the right. So I have the interval minus pi over 2, pi over 2. This is certainly in the domain. Pi over 2 has to be left out. And then we can take the interval pi over 2 to 3 pi over 2, etc. And then to the left we continue similarly, so then we have minus 3 pi over 2, minus pi over 2, union, etc. So that is the domain, and this is where f, which means tangent, is continuous. When are compositions continuous? F after g of x. When is this function continuous? So what you kind of need is, you would expect you need continuity of g, so that you can make the limit as x goes to a of g of x. So then this would be g of a if g is continuous. But then you sub this into f. So then f must be continuous at the value g of a. This is exactly what is true. So here's the corresponding result. So we assume that g is continuous at a and f is continuous at g of a, and then the composition f after g is continuous at a. And even we can write the limit as follows. So the limit x to a, f of g of x is equal to f of the limit of g of x. You can move the limit from the outside to the inside of a continuous function. This is really, really cool. Let's do some examples of this. Where is the following function continuous? Justify your answer. F of x is log 1 plus x squared. So I write this as a composite function. Now I use an h. I hope this doesn't disturb you too much. So I use an outer function h and an inner function g of x. So what is what? So h of x would then be log ln x, and g of x is 1 plus x squared. So what's about the domain of definition? H has a domain 0 to infinity, g has a domain minus infinity to plus infinity, and then we want to insert g into h. So we need to make sure whatever g is positive. Now we know that 1 plus x squared is always be bigger or equal 1, which is certainly positive, so we can always substitute it into ln. So then f of x is defined for all numbers, so it is continuous for all numbers. So you see, although the logarithm is involved, and the logarithm is only defined for positive values, since we insert another function g, and this other function g is always larger or equal to 1, we have no problem. So the domain of the combined function is indeed minus to plus infinity. Now, this example with the sine function is actually really funny. So I write it again as a composition using a function h and a function g. Okay, and then h would be the square root function, square root of x, which has a domain of non-negative values, and g of x is the sine function, sine of x, which has a domain of all real numbers. However, the range of g of x is the interval -1 to 1, which of course includes negative numbers, and then we get into trouble putting them into the square root. So where is the sine function positive? To find that out, I plot the sine function just quickly. So here, and then we have and then what is which? So here is pi, and this is 2 pi, 1 period, and then this is minus pi, this is minus 2 pi, the lower value is -1, the upper value is equal to 1. Well, and then you clearly see where the function is positive. It is positive here, and here, and here, and here. And so these are the bits which we are allowed to substitute into the function h. Then the domain of the composite function will be a union of all those highlighted yellow pieces. So in this case, f of x, which is h after g of x, is continuous on the following set of intervals. So the first interval is 0 to pi, union, and then comes 2 pi to 3 pi, union, etc. And to the left we have the union from, that guy is -2 pi. Here is -2 pi. So then this is -2 pi to -pi, union, etc. Let me summarize. The following functions are part of our zoo, which is polynomials, rational functions, root functions, trig functions, exponential functions, log functions, all our favorite functions. And we can add, subtract, multiply, and divide these functions to obtain continuous functions as long as we don't divide by 0. Compositions, if they are continuous, they kind of preserve continuity, so you can substitute one continuous function into another. And you look a little bit at the domain, and if the domain is fine, then the function is continuous.